The human brain is an amazing gray blob. Lightweight, lasts for decades, and most everyone has one. Computers are understandably jealous of our brains and like to imitate them with neural networks. Unlike the compact and portable brain that is powered by hamburger sandwiches, a modern large neural network requires its own power plant and countless servers. For software, all you need is PyTorch. Are you already well acquainted with tensors? If not, we recommend starting with our separate introduction. Tensors are the foundational building blocks of neural networks, so understanding them is essential. A tensor is a container for numerical data. Unlike lists or arrays, tensors are optimized for the computations required in AI and machine learning. They arrange numbers in n-dimensional arrays with a defined shape and data type. Consider the tensor X. This two-dimensional tensor represents a matrix, rows as data samples, columns as features. Run. Note the data type, floating point numbers, ideal for precision during computation. PyTorch tensors possess capabilities that ordinary number containers do not. They can reside on your GPU for accelerated computations. They also maintain a computational history. And most importantly for neural networks, they can compute their own gradients. But you must first enable this feature. Let me demonstrate the creation of a tensor requiring gradient tracking. Observe the requires grad parameter. When set to true, this tensor becomes self-aware of its own computational history. You can confirm that a tensor is managing its gradient by inspecting the requires grad parameter. Run. This feature will become paramount when we discuss backpropagation. Let us advance to the architectural overview of neural networks. Imagine training a machine to recognize pictures. Simple for humans, complex for computers. How do we bridge this gap? With artificial neural networks, mathematical structures inspired by the brain. Neural networks are composed of layers of artificial neurons. Real neurons exchange signals in the form of chemicals or electrical impulses. By contrast, artificial neurons exchange tensors, grids of numerical data. The architecture begins with the input layer, where data enters the network. Information then flows through intermediate layers, known as hidden layers. These layers perform mathematical transformations on the incoming tensors. Finally, the output layer generates predictions or decisions based on the processed information. Connections between real neurons are physical structures, called synapses. This is where signals are exchanged. In artificial neurons, these connections are replaced by mathematical formulas. Each connection is governed by a weight, a number representing the importance of that connection. Weights enable the network to amplify important signals while diminishing less relevant ones. Inside each neuron, the incoming signals are first multiplied by their weights and summed together. A bias value is then added, serving as the neuron's baseline adjustment. Finally, the combined result is transformed by an activation function. This step introduces nonlinearity, allowing the network to model complex patterns in the data. As data flows through the network, these operations occur in a sequence during a process called forward propagation. For image recognition, pixel values enter the input layer, traverse the hidden layers, and the output layer delivers a classification. But how do we teach a neural network to actually perform this task well? The key is to use examples, lots of them, where we already know the correct answer. By showing the network thousands of prepared examples, we can gradually adjust its weights and biases to improve performance. This adjustment process is called supervised training. After each prediction, the network calculates an error, called a loss value. This quantifies the difference between its prediction and the true answer. The goal in training is to minimize this loss. The method used to improve the network is called backpropagation. This technique calculates how each weight contributed to the error, then makes slight adjustments to reduce loss. So while forward propagation moves data through the network to make predictions, back propagation moves data in reverse to improve performance. This iterative cycle, predict, measure error, adjust, continues until the network reaches acceptable performance, or your patience with computational expenses runs out. Differentiation is at the heart of training neural networks. PyTorch simplifies this process with its Autograd system, which uses computational graphs to track operations and calculate gradients automatically. Let us start with a simple example: the cube of a number. We define a tensor, x, with gradient tracking enabled. This tells PyTorch to record all calculations involving x. When we define y equals x cubed, PyTorch adds this operation to the computational graph, but it does not compute any gradients yet. The gradients are only computed when we explicitly call the backward method. This method gets its name from back propagation, the algorithm used to train neural networks. During back propagation, derivatives are calculated, starting from the output and moving backward through the computational graph. Once we call backward, PyTorch calculates the gradient of y with respect to x for this specific input and stores the result in x.grad. Here, grad is short for gradient, which generalizes the concept of derivatives to higher dimensional spaces. For our example, with x equals 4, the derivative of x cubed is 3x squared, which gives us 48. And this is exactly what we find in x.grad. On to higher dimensions. Neural networks rarely operate on single numbers, after all. Instead, they handle tensors, multidimensional arrays. Here, we define a vector A with 2 components. Squaring each element of A creates a new tensor. But to compute gradients, PyTorch requires the output to be a scalar, a single value. A simple trick to achieve this is to add the components. When we call backward, PyTorch calculates the gradient for each component of A. Let us print the value of the gradient to see PyTorch in action. Run. If you compute the gradient of x squared plus y squared, you get the vector 2x, 2y. Evaluating this at x equals 4 and y equals 5 gives us 8, 10. And this is precisely what Autograd computed. Neural networks are constructed layer by layer. A layer is a collection of artificial neurons. Each layer applies mathematical transformations to the input data, passing the results to the next layer. A common approach is to have every neuron in one layer connected to every neuron in the following layer. These are called fully connected layers. We will create a network by subclassing the module class. This is the foundation for all neural networks in PyTorch. In the constructor, we define 3 fully connected, or linear, layers. Each layer maps an input vector to an output vector of a specified size. The first layer takes a 2-dimensional input and maps it to a 4-dimensional output. The second layer maps a 4-dimensional input to another 4-dimensional output. The final layer reduces the output to a single dimension, suitable for a prediction. At this stage, we are only defining the architecture. We will call the activation functions in the forward method. We also initialize the weights for each layer using a specific method to set them to random values, ensuring they are ready for effective training. The forward pass defines how the input data x flows through the network, layer by layer. Here, x is a 2-dimensional vector representing the features of each sample. First, the input passes through the initial layer, which maps it to a 4-dimensional representation. Then we apply the ReLU activation function, which replaces any negative values with 0. ReLU is one of the most widely used activation functions in deep learning. It is short for rectified linear unit, and simply sets all negative values to 0. This nonlinearity helps the network capture complex patterns in the data. Next, the second layer applies another linear transformation. reducing or amplifying certain features from the first layer. This is once again followed by ReLU activation, which removes any negative values introduced by this transformation. Finally, the third layer produces the network's output. Since we do not apply ReLU to the output, it can take on any value on the real number line. This makes the network suitable for regression tasks. Let us demonstrate how to use this model. First, we create a matrix to store the features for 3 samples, each with 2 features. Next, we create an instance of our model and apply it to the input data. As the input passes through the network, it transforms from a 2D input into 4D intermediate representations, and then into a single output value per sample. Finally, we print the output predictions. Run. Observe how the network has processed the input data, producing values that differ significantly from the input, evidence of the learned transformations applied by each layer. Now that we have a basic neural network up and running, of course, we want to improve it. And to improve it, we need to measure how well it works. For this, we will employ a loss function, which calculates the difference between the model's predictions and the actual target values. For regression tasks, a popular choice is mean squared error, or MSE, which magnifies larger errors, making them unmistakable. Observe. Using PyTorch's NN module, we define the MSE loss function as our criterion. In PyTorch's terminology, criterion refers to the loss function used to evaluate the model's performance. When we pass our model's predictions and target values through this function, it computes the average squared difference. Run. A perfect model achieves a loss of 0. Our model is not perfect. Knowing the error is only the beginning. To improve, the network needs a way to learn from its mistakes. Enter optimizers. An optimizer adjusts the model's parameters to minimize the loss. One fundamental optimizer is stochastic gradient descent, or SGD. The term stochastic refers to its use of randomly selected batches of data during training. Take note of the learning rate parameter. This hyperparameter determines the size of each adjustment. A learning rate that is too high risks overshooting the optimal parameters. Conversely, a rate that is too low results in painfully slow progress. Let us see how the loss function and optimizer interact during training. We begin by clearing any previously computed gradients. The loss is then calculated, and backward computes the gradients for each parameter. Finally, the step method adjusts the parameters to reduce the loss. Run. Observe how the updated predictions move closer to the target values, and the loss has decreased. Our model has improved. Now, let us combine all the components we have built into a complete training process. Training a neural network involves repeating the same steps over the dataset multiple times. Each full pass through the data is called an epoch, although they take much less time than the epochs you hear about in geology. We begin by generating our training data. Each input, x, y, consists of 2 features, and the target values are defined by the function x squared plus y. Next, we initialize the model, our simple 3-layer network with 2 hidden layers used earlier. We have, however, increased the number of neurons, so this example will be more thrilling. We then define the mean squared error loss function and an optimizer based on stochastic gradient descent. Before training begins, we record the initial predictions and loss of the untrained model for comparison. Run. The training loop consists of 3 essential steps, repeated 100 times. Forward pass. The input data flows through the network to generate predictions. Loss computation. The loss function calculates the error between predictions and target values. Optimization step. Gradients are cleared, New gradients are calculated using backpropagation, and the optimizer updates the weights. These steps refine the network's parameters, hopefully reducing the error with each iteration. Run. Observe how the loss decreases over time as the network learns from its mistakes. At the end of training, we compare the initial loss to the final one. Run. Notice how much closer the final predictions are to the target values. The improvement is clear and measurable, though perfect accuracy remains out of reach, a reality both for neural networks and for life itself. To ensure our model generalizes well, we test it on new data outside the training set. We then display the expected outcome, predicted output, and computed loss. Run. The network's prediction aligns closely with the expected result, confirming its ability to learn and generalize from the data. Conclusion. This process mirrors learning for rational humans: predict, evaluate mistakes, and adjust behavior. Though unlike humans, the network completes this process in just 100 iterations, all without coffee breaks. Congratulations, you have connected the dots, layer by layer, neuron by neuron, to create your first neural network. From activation functions to optimization steps, you are now equipped to build models that learn and adapt. May your weights converge, your losses decline, and your networks align with predictions divine.